Alright, now we're going to talk about the correlation coefficient, okay? And your learning target is I can determine and interpret the correlation coefficient. So first, a definition. The correlation coefficient is a number, and it's between -1 and +1, -1 and 1. This number describes how close the data points are in, given a table or given just some data, how close those data points are to the line of best fit. Okay, and so there's certain properties of the correlation coefficient. Remember that number R, we're just going to call it R, is if it's between -1 and 1, but if R is equal to 1, that means the data set forms a straight line, okay? So the data is in a straight line with a positive slope, okay? If R is equal to 0, then the data really has that blank is no correlation. And if R is equal to -1, then the data still forms a straight line, but it has a negative slope, okay? So if we get R to be negative at all, then we're going to have a negative slope. If we have R as positive, then we have a positive slope. Alright, so for example 1, it says the table shows the relationship between a city's population and the average time the city's citizens spend commuting to work each day, okay? And so we're given a list of a bunch of different cities, how much the population is in thousands, and the average commute time in minutes, depending on what city we're talking about, okay? So the very first thing we want to do is we want to find an equation for a line of best fit. And you remember what we did is we went to our calculator, and in order to get there, you press the stat button. Okay, stat is this button right here. Stat, you press enter at edit, and we have a list 1, a list 2, on and on and on to put those numbers in, right? Now, our first list we're going to use as the population, okay? So I'm going to move this over here, and let's just kind of move things around a little bit. Our first list, we're just going to go all the way down this list and put all these numbers into list 1. So we have 505, 486, 710, 630, 2833, 146, 2144, 553, 8496, and 223. Okay? Now for list 2, we're going to put in the same exact thing, except this is going to be the average commute time. So 21.5, 31.1, 23.2, 25.1, 30.6, 17.9, 27.7, 25.2, 34, 24.2. Okay, and you should see that these are going to match up now. Okay, now in order to find the actual what the equation for the line of best fit is, remember we go back to stat, and we're on edit. We want to move over to calculation now. Okay, and to go to the calculation, we want to go down to number 4. That's the linear regression. Remember, that's exactly what we did in the last video. You press enter, and last time I said that you needed to do list 1, list 2. That is a very good thing to do. If those are the only 2 lists that you're given, you can just press enter, and you're given this number right through here. Okay. Now, if you get a number like this, our diagnostics aren't on. So what you have to do is you have to press second, and you got to go down to catalog. That's 0. Okay, right through here at 0, it says catalog, and scroll down to diagnostics on. Okay, so you're gonna have to go all the way down to where it starts with D, diagnostics. We want those to be on, and all you have to do is press enter and press enter again. When it says done, you're good. Now if we go back, press calculating, do list 4, press enter again, we get a little bit more information, which is what we wanted. Okay, so to find the equation now, I'm going to scroll this down a little bit. We know we're trying to use y equals mx plus b, and we've got a as 0.001. Okay, so y equals 0.001x plus our b, and our b is 23.8 plus 23.8. Okay, and remember this is about. Okay. Okay, now to tell how well the line fits the data, we use R, okay, that special number R. And this is our correlation coefficient, 0.71196. Okay, let's take that to the 4th decimal point there. We can say pretty good as far as how well the line represents the data. Our correlation coefficient kind of measures that. Pretty good. We're at about 0.711. Okay? So you see that correlation coefficient, essentially what that does is it measures how good the data is. By this correlation coefficient of 0.711, that's pretty strong. And you know that because that correlation coefficient is positive, we're going to have a positive slope. And it just means that the closer you are to 1, the more the data is all in the exact same line. Okay, example 2 says that there's this table that shows the test averages of 8 students. The equation of the least squares line for the data is y is approximately 0.77x plus 18.12, and r, our correlation coefficient, is at 0.87. Okay, all we have to do for this is discuss the correlation and causation for the data set. So first, let's discuss the correlation, and we can see that the correlation is positive. Is positive and strong between, this is a lot of writing now, between U.S. history and science test scores. Okay, that describes the correlation. We have a strong correlation between the test scores of U.S. history students and science students. Now, the causation part of it, causation is asking, is there some sort of cause and effect here? If you do well on a U.S. history test, are you going to do well on a science test? If you do well on a science test, are you going to do well on a U.S. history test? And our answer to causation for this is there does not seem to be causation. Just because you do well on a U.S. history test doesn't mean you're going to do well on a science test, right? However, there is no proof of causation. Students' test scores in one subject do not affect this test scores in another. Okay, and that's just where you have to know what type of thing is happening here. You have to understand the example, and that's what you're proving to me here is if you understand what correlation and causation for a certain situation is, then you're on the right track. Okay, that's it for today.